Hello students, I am Chakraborty from Department of Geology, University of Delhi. Today our topic of discussion is reservoir petrophysics. As you know that we geologists, we always are interested about rocks, and when we will be discussing the rock reservoir petrophysics, we will be able to know that what we call the subject petrophysics, how it is related to the void spaces of the rock, which we normally refer to as porosity, and how the pores they get interconnected, and that gives the rock the quality that is called permeability, and how porosity and permeability, these two combinedly control the rock petrophysics and the capability of a rock to hold the oil or gas, that is hydrocarbon. You will also be able to know the different effects of the rock characters, such as the grain size, their sorting of grain, all these what kind of effect it put on the rock porosity and the permeability. We will also discuss the different kinds of porosities that you come to know, what is called primary porosity, the secondary porosity, and like that. So, if we now go back, that what really provokes us to talk about reservoir petrophysics, because as a geologist, as I have already told, we are interested about rock. But the rock petrophysics essentially is not really the whole rock. Here our interest is about the holes within the rocks, that we call the void spaces within the rocks, and that we refer as the term called porosity. So, porosity is essentially the void spaces within a rock, and these void space, their geometry, their interconnectivity, their different kind of pore throat geometry, all these things together, that gives the rock the quality what we call the porosity and the permeability. Now, this porosity and permeability essentially gives a rock reservoir quality, but it does not in any way gives a guarantee that the rock really has the physical presence of oil or gas. As we know, for the physical presence of oil or gas, you require a petroleum system development, where you have source rock, where you have cap rock, and also you have a reservoir rock. In this module of discussion, our intention is to discuss with you what really gives the reservoir quality in a rock. Now, coming on to the clastic rock. What we know that any kind of clastic rock, or what we call the terrigenous rock, we have the three different components, that is the framework, matrix, and cement. Now, if I describe this by a figure, it will be more helpful for you to know what really I mean by the matrix, framework, cement, and the porosity, as well as the interconnectedness of the porosity. Now, this is a very simple drawing for a sandstone, and what we can know, there are three different kinds of components in a sandstone. One, what we call the framework. It is like our body, that what is the framework of our body? The bones are the framework of our body. Similarly, in a sandstone, these larger grains, they form the framework of our body, of a sandstone. And the fine grain particles which remain between the larger grains, that we refer to as the matrix, which is also terrigenous in origin as the larger grains. But the precipitated material around the grain, what is formed after the deposition or during deposition by the chemical precipitation, but not by the terrigenous supply, that we call the cement, which may be what normally in a sandstone, it can be a quartz cement, it may be a ferruginous cement. and these three together makes a sandstone structure. Now, if you see that this may be this may be the cement on it, and there is a gap, so this becomes a porosity, and there lies another porosity which is the open space, and if these two porosities that is interconnected, then we call it a effective porosity. And if suppose I have another, now come on to this case where this is the boundary of this grain with cement, this is the boundary of this grain, and this is the boundary. So, there is a void space in between. But this void space is not connected to any other void space. So, this void space is the unconnected void space, unconnected. This will definitely add on to the total porosity of the rock, but this porosity will not be an effective porosity of the rock. The effective porosity is that when the porosities they are interconnected, but the total porosity that concerns both interconnected and unconnected porosity altogether. So, if we define what is called porosity of a rock, then we define that it is the volume of the void space, we call the volume of void space divided by total volume of rock into percentage. Now, that is what is called porosity, and as you see it is a volume divided by volume, hence the porosity never has any kind of unit, but it is expressed in terms of percentage. Now, once we discuss this is basically the porosity, it always becomes a concern that how much the porosity that will be depending on the different factors of a clastic rock. We will discuss that how the porosity in a clastic rock, how much that is originally depositional in origin and how much that porosity that is formed after the deposition of the rock. So, according to the depositional history of the rock, porosity can be broadly classified into primary porosity and the secondary porosity. The primary porosity is that porosity which is formed during the deposition of a rock, and secondary porosity is that which is formed after the deposition during the diagenetic history of a rock. The primary porosity, it is very important in case of a clastic rock such as sandstone, which is often very high during its depositional stage, but during its further maturation after the deposition it normally decreases. And that decrease in the primary porosity, that is related to two major factors. One is the compaction of the rock and second is the lithification of the rock. So, these two factors that decrease the primary porosity of a rock that is formed like a sandstone which is originally deposited. We get though very nominal amount, some amount of secondary porosity also. So, if we see that what really is the nature of primary and secondary porosity during the diagenetic history, what we find that for any sandstone which depositionally it contains a porosity about 35 to 40% for any sandstone normally, and when it goes to burial there are different stages of diagenesis of a sandstone, what we normally say that is the immature stage, then the submature stage, the mature stage and the supermature stage. And the primary porosity, if it starts from, if it is 10, 20, then this becomes 40, this is 30, this is in percentage. The depositional porosity, it is more than 30%, then with the by the end of submature stage, that the porosity significantly decreases, the primary porosity significantly decreases, and that is because of the effect of the compaction and some effect of the lithification. But the secondary porosity is always very low in the initial stages, as you can see, but only during the mature stage you get a sudden increase in the secondary porosity in some of the sandstones, which normally has a calcareous cement or carbonate cement. Now, why there is a sudden increase at certain stage of the secondary porosity in a sandstone, and that also such a deep level in the mature stage? The reason is that any organic matter which is present within the sandstone, that organic matter also gets matured with the burial under the depth, and that goes into the decarboxylation stage, releasing carbon dioxide at this stage in the water, which makes the water acidic because of the release of carbon dioxide, and that acidic water leaches the carbonate cement which might have been present within the sandstone at the beginning. So, that leaching of carbonate because of carboxylation of the organic matter at the deeper level with the maturation of organic matter, that basically cause the development of some amount of secondary porosity in the sandstone. If we see that what really controls the initial depositional porosity of a sandstone, the original depositional porosity of the sandstone, is it really depending on the grain size? If there is a coarse grained sandstone is a fine grained sandstone, I should get the more porosity in fine or the coarse? No. Porosity never depends on the grain size of a rock. If we have spheres of different size but all of uniform size, then a larger sphere will create the same porosity as that of the smaller sphere. And that is a very major observation, that the porosity does not depend on grain size, but the porosity depends on the grain packing. Definitely the grain packing has a big role in what will be the original depositional porosity. A cubic packing, that will result in the porosity of about 48%, whereas a rhombohedral packing, that results in a porosity of 26%, irrespective of what is the size of the sediment. Of course, porosity depends on the sorting of the rock sediment. Now, if the sorting is poor, the porosity will be low. What is the reason? Just because the smaller grains, they will occupy the pore spaces between the larger grains, and thereby it will be decreasing the porosity of the rock. Whereas more better the sorting, higher will be the porosity of the sediment and also the rock. So, this is essentially a result of what the size does not have a much role in the porosity, whereas the sorting has a significant role in the porosity. Porosity also depends on the grain shape. The more rounded the porosity, the more rounded the grain, the porosity will be less, and less rounded the grain, that will be creating the more porosity. This is typical when you get the original depositional porosity of mud is more than that of a sand. Why? When I tell that there is no role of the grain size on the porosity, then why the porosity in mud will be more than the sand? The reason is that the mud grains are more angular than that of sand, and that is why the mud grains, when they settle, they make a point contact with respect to the sand grain, they will more become a surface or the line contact, and that point contact causes the more porosity within the mud. It is not the size. Size is not the effective there. Now, once we discuss that this is the effect of the porosity, then I want to discuss with you in a graphical form what really the effect of the size and the sorting on the porosity and the permeability. So, this is a diagram which basically talks about that how the grain size and its sorting that affects the porosity and permeability of a sandstone. if you see that this is what is the grain size I have shown, that is the very fine to fine, medium and coarse, and these are the lines which define the boundary between very poor sorting, medium sorting, well and very well sorting. Now what you can see that the very fine, this is a grain size. So in this size, if you have the sorting value that is changing, in the size the sorting value that is changing, and then that the change in the sorting value, that will cause a large effect on the porosity of that grain size. And also the permeability, that will be widely varying, because if this is a line, that is the poor sorting, and then from fine to coarse, the different grain size will have the poor sorting, the different permeability value. So this figure clearly illustrates that the effect of the size and the sorting on the porosity and the permeability of a clastic reservoir. Now once I discuss this, then we will discuss what really we mean by the primary and the secondary porosity. Now primary porosity, that is the porosity which is formed during the deposition of a sediment, and it essentially is the two broad types. One is called interparticle, and we call it intraparticle. Interparticle, that is very common in sandstone, where you get the porosity between the framework grains, which I have already discussed with you, that between the framework grains the porosity is formed, we call it interparticle, and which basically follows whatever I have discussed till now, that its original depositional porosity depends on packing, then the effect of the size, the sorting, all these are applicable in case of interparticle porosity, which is very common in sandstone. Intraparticle, that commonly we get in a carbonate sand, that any carbonate sand, then we get the body chambers that act as a interparticle porosity. So in case of any intraclastic carbonate, where you get the bivalves, the gastropods, you get the ammonoids, you also get the brachiozoa. So all these things, they have their body chambers which essentially acts as the interparticle porosity, which often get filled subsequently by the micrite, that is the infiltration of micrite, or they may get modified during the diagenetic history because of mineralogical instability. But suppose I have a gastropod, I can also have, so you can have the chambers, there may be the pore spaces. So these are nothing but what we call the intraparticle porosity, which is very important porosity in many of the carbonate reservoirs. Now coming on to secondary porosity, which is formed after the deposition, secondary porosity. It also is a different type, suppose intercrystalline, then you get fenestrelle, you get moldic, vagi, also we call it cavernous, and we get the fracture porosity. All these that come under the domain of secondary porosity. Now interparticle porosity we get in the igneous rock, we also get some of the recrystallized dolomite, we get in the evaporite, where you get the recrystallization and the complete crystallization that causes the intercrystalline porosity. Of course, this porosity, it has a planar fabric, this porosity, that is the advantage of it, but normally this porosity is very, very minimum in case of a igneous rock or in case of a evaporite. So this is in very rare cases, this intercrystalline porosity also can be of very use if it is subsequently increased in size by means of dissolution. Fenestrelle porosity normally we get in lacustrine carbonate sediment in the homogeneous mud. In here essentially what we get, that because of the decay of organic matter and the gas escape, we get the porosity which is more than the fabric of the sediment. So if I have this kind of a situation, that we have the sediment grains like this, and then you start a opening like this. Then these are the opening, and the size of the grain, that is something like this. The size is more than the fabric size. Then you call it a fenestrelle, and this normally indicates that the decay of organic matter and the escape of the gas, and that is very common in the lacustrine carbonate, in the homogeneous mud and all this. Some of very typical kind of these fenestrelle porosities, it is also referred in literature as a bird size structure, and this is a typical product of the intertidal to subtidal flat of carbonate, which get exposed recurrently with the tidal effect. Now we get the moldic porosity. Now moldic porosity, it is a fabric selective porosity. What I mean by fabric selective porosity, that any carbonate rock, as you know, it is made up of some allochemical constituent and orthochemical constituent. Now allochemical constituent, and we have different type. You can have a void, you can have a bioclast, you can have a intraclast, you can have all these are basically the allochemical constituent. And so the orthochemical constituent, they are basically the micrite and the sparite. Now if I have in a carbonate, I have some bioclast, some void, these are some paloid, and then it is cemented by sparite. Now as I have said, this is fabric selective. Suppose only voids, they are going into solution, no other thing is going into solution, because the void is mineralogically unstable, so it is going into solution. So what will happen, this void, it will go into solution, it will go into solution, and that will create the opening of the porosity, but the rest of the part is not disturbed. So it is fabric selective. So I can have a large amount of porosity that can be generated by this moldic porosity. If only voids, they are going into dissolution, we call it moldic porosity. If the bioclast only going, we call it biomoldic. If the paloids are going, that the pale moldic. So all these but this porosity normally is not interconnected. So effective porosity will never rise, but the absolute porosity may rise in it. So that is the beauty of it, that it is a fabric selective which can increase the absolute porosity but not increase the effective porosity. Now coming on to the bhagi and the cavernous, it is larger than the moldic porosity, and it is not a fabric selective, and it is larger, and it can take into dissolution a number of things together, and that is the beauty of the bhagi or the cavernous. It is only the question of scale, that whether I call it bhagi or I call it a cavernous. The larger scale is called the cavernous, which has a lining of the of precipitated sediment in the lining in the form of the bhags or the cavern. Now coming on to the fracture porosity. The fracture porosity is also very important kind of porosity, which we may get associated with any kind of the tectonic disturbance or any release of the overburden pressure. We get the fractures which may be subsequently healed up. We also get fractures which may be subsequently opened up. Definitely the healed up fractures, it will not be a very important thing for us, but the fractures which open, that is a very important for us. We get fractures associated with some kind of compression, that is the sliding, slumping, there can be some fractures that is developed. We also get fractures, tectonic fractures associated with the compressional fold structure, that is along the axial plane you can have some tensional fracture, or we can also develop the shear fractures associated with the folding. So all these fractures, they finally help in the increasing the permeability of the sediment or permeability of the rock, unless it is healed and it is filled subsequently. In some of the source rocks where the porosity is sufficient, but we do not get sufficient the permeability, then we create the artificial fracture by the which is called the artificial permeability recharge by means of the artificial fracturing. Now we will come into the role of this total porosity and the permeability in the total emplacement of the hydrocarbon in a reservoir. Before we go into that, let me also discuss with you what is called the permeability. So, here we are discussing permeability, and this is the simple law of Darcy, what you might have seen in many other modules, including the hydrogeology. People always discuss the Darcy's law to talk about the movement of any kind of fluid. Now, what Darcy's law say, that the total amount of fluid that is moving, that is actually dependent on the cross section and inversely proportional to the length, and it is dependent on the pressure gradient, that is the pressure difference. So, we get the Darcy's law, and that Darcy's law essentially defines the parameter what is called the permeability, that is referred to as the K, that is the permeability. And this permeability, what we talk about from the Darcy's law, that is the absolute permeability. And absolute permeability, when we talk about, there are some premise which makes the Darcy's law valid. This number one, that the entire reservoir, it is filled by a single fluid, 100% saturation of a single fluid. Number two, that the entire flow is in the laminar range and there is no effect of the any other fluid in the system, which may be true when it is a single fluid system, but in most of the cases when the hydrocarbon is there, it is not a single fluid system. We get water, we get oil, and we get gas. So, it is a multi-component system. And when you talk about the multi-component system, then the question of relative permeability and the effective permeability, these two basically comes into picture. So, the effective permeability and the relative permeability, that is basically applicable when we have a multi-component system. Effective permeability is the permeability of the single component out of the total permeability. So, if I think of the permeability of water, permeability of oil, permeability of gas, so all these separately, these are the basically the effective permeability. And if you combine the three, that is Kw plus Ko plus Kg, this will always be lower than the value of absolute permeability K. And what is relative permeability? Relative permeability is the permeability of a single component divided by the absolute permeability. That is what is the relative permeability. So, once we know about the porosity and the permeability, which depends upon the interconnectedness of the porosity, then we will see that how really the fluid saturation in a reservoir and the behavior of oil and the water, that makes any system as a reservoir depending on the porosity and the permeability. Now, for this I draw a diagram which will explain you that the concept of the relative permeability. Okay, now we have learnt about the relative permeability. We will now discuss the capillary pressure curve, which basically explains the effect or the role of oil when it replaces water, how much the oil is necessary to replace water so that the reservoir starts behaving like a oil producing reservoir. Now, you see, this is the relative permeability curve for the oil, and this is the relative permeability curve for water. Now, this, when we say the relative permeability curve of the oil, then you can see that the almost the relative permeability of oil becomes 100% as it reaches here, and the entire thing is replaced. So, naturally any reservoir, that is water weight. So, all the pore spaces, they are occupied by water. when oil starts entering into it, it first starts replacing water in the largest sizes of the pores where the capillary pressure is minimum, and therefore it becomes easy for the oil to expel the water from the larger pores to the smaller pores. So, the oil pushes the water into the smaller pores where the capillary pressure becomes very high, and it does not possible for the oil to replace the water in that. That water, that point, that up to which this replacement of water is not possible, that is in this case is the 30%, nearly 30%, that pore space which cannot be replaced by the oil, Now, if you see the capillary pressure, that this is the water which cannot be replaced, and we call it irreducible water. Now, this one that shows that how oil is entering into the pore spaces and replacing the water. As long as that the oil replacement of water is less than 20%, the reservoir will only produce water without any oil. Once oil replaces water on up to 15 to 20%, then the system it becomes from water weight to oil weight, and then some portion of the oil production it starts. But at a certain time when the oil significantly replaces the water, the capillary pressure curve which abruptly increases. That abrupt increase of the capillary pressure curve, that indicates that the oil it is basically replacing the water and taking the pore spaces within the reservoir. Even then, this much portion what is shown, that pore space cannot be replaced by oil, which will be always occupied by the irreducible water. So, this capillary pressure curve, that is a very good indicator that how is the porosity and the permeability, and that is acting as a passage of the oil and replacing water in the pore spaces, and the effective pore space up to which the oil can replace the water, and that reservoir can produce oil. Now, after this discussion, what we come to know that there is something what is called the permeability of a reservoir. Now, this permeability again is not a homogeneous in all direction of a reservoir. The permeability also is divided into two components, what is called the horizontal permeability and the vertical permeability. Horizontal permeability is always higher than the vertical permeability because of the orientation and the arrangement of the grain. And commonly in any reservoir it is found that the horizontal permeability and the vertical permeability ratio, it varies from 1.5 to 3, in cases it can go almost up to 10. So, horizontal permeability and the vertical permeability, that does not remain same, and any reservoir that do not totally behave in a homogeneous manner in terms of the permeability. We can also see that the different kinds of rocks, they in terms of porosity and permeability behave differently. In a figure it is shown that we can have very low porosity permeability. Suppose when we see a basement, we can have very high porosity but very low permeability. If you see a carbonate reservoir, particularly when the carbonate reservoir is showing mainly the moldic porosity, we can also have the porosity and permeability, they are going at par. That is when we get the clastic reservoir, and we can have a very high permeability with a very low porosity when you have a fractured reservoir. So, all these, they are the different porosity permeability I can have in a nature, and that is causing the huge heterogeneity in a reservoir character and reservoir petrophysical character. So, once we have discussed all these things, if I summarize the discussion what we have made, that the pore spaces and the volumes, that is the void spaces in a rock, that basically refers to porosity, but all porosity is not effective because many pores, they may be not interconnected. Porosity can be primary and the secondary. In case of sandstone and the clastic rock, primary porosity is the main type, whereas in a carbonate rock, secondary porosity can make a large role in the total porosity. In case of porosity, primary porosity, that the interparticle porosity, that the sorting of the grains, shape of the grain, they have a major role to play, though size does not have any role to play. And also what we have seen that the capillary pressure curve that help us in identifying that how the different phase saturation and its behavior when one phase is replacing the other, and the pore throat geometry, how it is controlling what will be the effective porosity in a particular reservoir. We also have discussed that what kind of reservoir will have different kind of porosity and permeability, what is called the absolute permeability, the effective permeability and the relative permeability. With all this discussion, I believe that you have some idea that what really controls the reservoir quality of a particular rock strata. When we talk about the reservoir quality, we basically talk about the porosity and permeability of the rock strata. But that does not give guarantee that whether there is oil or not. The oil, presence of oil or gas in that reservoir which makes it a trap, it requires the availability of source rock, it requires the availability of cap rock, which will cause the entrapment of the oil within the strata, then I call it a trap. Also, it is important that the capillary pressure or the height of the oil column above the oil water contact. What is the height of the oil column? If my entrapment or the trap, it is lesser than the height which is required for the emplacement of the oil and replace of water, if the trap height is less than that, even then the oil, if it is available, it will not be entrapped. So, the entrapment height needs to be always higher than the height that we require above the oil water interface to replace the water by oil. So, I expect that this discussion will generate some interest in you to go further in understanding the dynamicity of the system in terms of the character of the rock, that is the property of the rock, that is the porosity, permeability and the behavior of different fluid phases. And you will further learn all the details about this in the references given with the text. Thank you.